Morning guys, we are Group钻石王老五. Today we'll present our project on improving the material flow resilience of Huawei's Ascend 610 AI chip. Our group wants to emphasize one key message from the beginning for Huawei's automotive business. Success depends not only on how advanced the chip is, but also on whether the chip can be supplied continuously and reliably. In other words, strong technology must be supported by a strong supply system. At present, the supply chain faces several clear bottlenecks, including heavy reliance on SMIC's 40nm process, a capacity gap, a relatively low yield rate, and the delivery delays. This problem shows that Huawei is facing not just a manufacturing issue, but a deeper resilience issue. So our group does not only focus on how to increase production, more importantly, we'll ask how Huawei can build a supply chain that can better resist the shocks, reduce dependence, and recover faster. That is the main value of our idea. The issue is especially important because Huawei is transforming from a telecommunication giant into an intelligent automotive solution provider. In this strategy, the Ascend 610 chip is a computational core of advanced driving system. So it's like the digital heart of Huawei's automotive business. That means once the chip supply becomes unstable, the impact goes beyond production efficiency. It can directly affect vehicle delivery, customer confidence, and Huawei's future competitiveness in the intelligent vehicle market. So what is the material flow resilience? Our group defined as the ability to maintain a stable flow from wafers to finished modules under disruption and to recover quickly afterwards. It includes three dimensions: resistance, absorption, and recoverability. Resistance means avoiding single point failure. Absorption means buffering shock through inventory and planning. Recoverability means restoring flexibility through innovation and adjustment. This concept is important because it shows that resilience is not just about solving today's problem, but about preparing Huawei for future uncertainty. Based on this idea, our report will continue in several parts. First, I introduce the background and the concept of resistance, and then my teammate will explain the material flow structure, identify the major risk, analyze the financial constraint, and finally present our improvement strategy. Overall, our key message is that improving resilience is not just about surviving disruption. It's about sourcing Huawei's long-term competitiveness. Thank you, and now let's move to the next part.
Hi everyone, I'm Li Ziyuan, a student responsible for the second part. Today, I will analyze the material flow of Huawei Ascend 610 automotive-grade AI chips, revealing its key links and potential risks. The Ascend 610 has a clear defined three-tier supply structure and is a complex network built through the collaborations of 3 layers of suppliers. Tier 2 basic materials supply serve as the starting point, offering a wide variety but with relatively low technological barriers. Tier 1 core manufacturing and processing is the core of the supply chain with very high technical barriers. Huawei, as the overall solutions design and system integrator, is responsible for end-to-end quality control and interacts directly with end customers. In terms of materials circulations, a linear closed-loop chain is formed. Raw materials supplies across the country deliver materials to SMIC, Beijing or Shanghai factories for chip manufacturing, which are then sent to GCET for packaging and testing. And finally reach Huawei's Dongguan manufacturing center for assembly, eventually flowing to automobile companies. The in charge relies on the land transportation networks and intelligence logistics scheduling systems, and any interruptions in any link will halt the entire materials flow. It is particularly noteworthy that this supply chain adopts an extremely comprises zero inventory strategies. SMIC's finished goods warehouse maintain a safety store of only 2 days, where Huawei's Zhongguan raw materials warehouse has achieved a turnover cycle of only 7 days. Although these strategies reduces inventory costs, it also makes the supply chain highly fragile and imposes very high requirements for emergencies in response. Finally, we identify the 3 core bottlenecks. First, the capacity utilization rate is long-term saturated, exceeding 95%. Second, the automotive grade yield rate is relatively low, only about 70%. Third, there is 100% dependency on single suppliers. These factors together constitute the key risk points of the current material flow.
Today I will present our analysis on material flow resilience risks for automotive chip supply chain based on the probability impact metric framework. This metric helps us objectively judge each risk by 2 dimensions: how likely it happens and how severe the impact is, so we can prioritize responses effectively. Let's go through the 5 key risks. First, geopolitical sanctions on SMIC show high probability and medium impact, so we mark it as high attention risk. Second, sole source dependency on SMIC is the most critical one, high probability and critical impact, making it our top risk. Third, production line malfunction is low probability but high impact, so we need solid contingency preparation. Fourth, capacity diversion to Huawei smartphone chips is medium probability and medium impact, requiring continuous monitoring. Fifth, insufficient automotive guard packaging and testing capacity has medium probability and high impact, so it's our improvement priority. This metric clearly shows our risk landscape and where we must focus. Now let's look at the core problem and real impact. The root issue is clear. SMIC is our only foundry. Any production change or disruption directly transfer to downstream automotive clients. Worse, we face a risk superposition effect. Geopolitical tension, capacity diversion, and packaging bottlenecks happen together, leading to extremely low material flow resilience. The vulnerability brings 3 serious consequences. First, longer lead time and frequent delivery bottlenecks. Second, disrupted production schedule for our automotive partners. Third, unstable performance in automotive AI sector. In one sentence, any major disruption at SMIC will break our entire production and supply system. Let's see the third part, the conclusion and strategic directions. Finally, let's summarize our conclusion and strategic directions. From the analysis, we confirm 3 quick conclusion. That's third. And to fix these vulnerabilities, we respond 4 actionable strategies. First, qualify and
alternative foundries to achieve material process, multi-sourcing and reduce single-source risk. Second, build safety stock and buffer capacity to absorb supply shocks. Third, strengthen cooperation with packaging and testing facilities to expand automotive-grade capacity. Fourth, regularly update the probability impact metric for dynamic and proactive risk management. These steps will significantly improve our supply chain resilience and ensure stable support for automotive business. Thank you.
Diagnosis and analysis from a safety stock model view. First, let's talk about the three main steps of our analysis. The first one is data diagnosis, and we collect and calculate historical inventory data and order lead times and demand changes. This gives us solid data for later analysis. The second is model application. We use the safety stock model to compute the needed safety stock. Then we find the gap between their interval and the best target level. The third is the root cause analysis. We look deep into the difference from the model. We find the real reasons like stable supply delays or wrong demand forecasts. And now let's see the main problems we face. First is the core bottleneck. The biggest problem is capacity shortage at SMIC. This makes supply lead times very unstable and much longer. Second, supply risks. Unreliable delivery from upstream raises supply risks. It messes up material planning and reduces the flexibility of our material flow. And third, when capacity is tight, this happens. Not enough capacity and longer lead time and higher inventory and more resources taken. And last, the worst supply instability. And this circle makes our problems even bigger. And we use a simple but clearly formula for safety stock. For automotive ASIL chips, we use Z equals to 3, which means 99.9% service level, and 0 is the standard deviation of delivery demand. We use 200 units per day for normal market changes, and the lead time is the average days for order to delivery. Next, we compare the two situations. When supply is stable, about 3,288 units are enough to keep high service level, and when lead time doubles, the SS equals to 4,650 units. Because of capacity issues, required safety stock increased nearly 42%. This shows longer lead time shortage purchases up safety stock. The relationship is non-linear, and as the lead time goes up, safety stock raises quickly to cover supply uncertainty. And finally, we have 4 key conclusions. The first is the main issue is inflexibility, supply and long lead time, not demand uncertainty. The second is higher safety stock uses too much working capacity. It limits our finance flexibility. And the third, more inventory takes up scale warfare capacity. This makes the production bottleneck even worse. And fourth, we have less ability to build backup stock or use dual sourcing. This seriously hurt supply chain resilience.
Hello, my name is Zhang Jinyan, and I will introduce the Part 5 Matters Analyze. CMIC is the leading integrated circuit manufacturer in mainland China with the rise of AI. It has made a strong progress in AI-related chip fabrication. After Huawei partnered with CMIC, favor supply for Ascend 610 became more reliable. Previously, Huawei depended on overseas foundations. Domestic control reduced risk from policy changes and cross-border transport. Long-term cooperation stabilized production and pricing. By 2025, CIMIC's capacity will reach 45 to 50,000 wafers per month, and rise to 60,000 in 2026, giving Huawei room to expand ASIC chip production. G-Site is China's leading packing and testing company. It has achieved breakthroughs in chip-light technology and slow bottlenecks in advanced process. G-Site is the only domestic provider capable of mass production. By handling Huawei's high-end orders, it enabled the full packaging workflow of ASIC chips to completed in mainland China. This closed loop avoids customer delays and shipping risk. The cycle is shortened from weeks to days, making material flows more flexible when demand changes. In conclusion, Huawei's localization strategy in wafer fabrication and packing testing break upstream and downstream bottlenecks, enhance resilience and flexibility of material flows, and provides a solid foundation for future AI chip growth. That's all. Thank you for your listening.